You can know every reaction on the exam and still get the mechanism problems wrong if you can't answer one question. Who is attacking whom? If you can identify the nucleophile and the electrophile, you've already solved half the mechanism. Hey there, ninjas. Before you draw a curved arrow, before you predict a single product, before you even think about a memorized reaction, you should always ask this: who is the nucleophile and who is the electrophile? Because if you answer those questions correctly, the mechanism becomes much easier. And if you answer them incorrectly, it almost doesn't matter what reaction you're doing, because everything that follows will likely be incorrect. There aren't many skills in organic chemistry that I consider non-negotiable, but finding nucleophiles and electrophiles is definitely one of them. There are many textbook definitions for nucleophiles and electrophiles. For nucleophiles, the one that I find to be most intuitive for students is nucleophiles are molecules with excess electron density. Likewise, an electrophile is a molecule that somehow lacks electron density. We sometimes call nucleophiles electron donors and electrophiles electron acceptors, and we sometimes use the terms nucleophiles are electron sources and electrophiles are electron sinks. And all of those definitions sound nice, but how am I supposed to use it on an exam? To find a nucleophile or an electrophile, we can ask ourselves a couple of questions. For the nucleophile, we can ask, is it negatively charged? Is it rich in lone pairs? Does it have pi electrons? If yes, then that molecule is probably the nucleophile. For an electrophile, we can ask, is it positively charged? Is it a Bronsted acid? Or is it attached to an adjacent electronegative element that pulls electron density away? If you find a molecule that meets some of these criteria, that molecule is probably the electrophile. Let's look at an example. The reaction between ethyl bromide and hydroxide. Hydroxide has a negative charge and lone pairs of electrons. Hydroxide is the nucleophile. Ethyl bromide has a polar carbon-bromine bond where carbon is partially positively charged. Ethyl bromide is the electrophile. That's it. Before drawing any arrows, you've already identified the roles. But now let's zoom in. Saying that a molecule is a nucleophile or a molecule is an electrophile is nice, but which atom is doing the attacking? Which atom is being attacked? Let's look at hydroxide. Which atom is the nucleophilic atom? It's not hydrogen. It's the oxygen that is negatively charged, electron-rich, and the nucleophile. That's the atom that donates electrons. That's the nucleophilic atom. Now let's look at ethyl bromide. Which atom specifically is the electrophilic atom here? Students will often point at bromine because bromine looks important. But bromine isn't the attack target. The carbon in this polar bond is the partial positive carbon. The carbon is the one adjacent to an electronegative element. The carbon is the electrophilic atom in this molecule. When the nucleophile attacks, that's where the nucleophile will attack. So every step in just about every mechanism boils down to two atoms. One atom with excess electron density, that's the nucleophilic atom, attacking one atom that lacks electron density and is the electrophilic atom. Find those two atoms and most mechanisms become much easier. To finish out this mechanism then, the nucleophilic oxygen atom will donate its lone pair of electrons to the electrophilic carbon atom, forming a new bond between oxygen and carbon. That would be a fifth bond, too much electron density around that carbon, so we break the carbon-bromine bond. The bromine leaves with a lone pair of electrons as a leaving group. That's beyond the scope of this video, but our product for this reaction will be ethanol as our major organic product and bromide as the byproduct. Now let's level up our ninja skills and let me show you the real OChemNinja shortcut. Because here's where students get overwhelmed. Many functional groups can react in multiple ways. The same molecule can both have electrophilic sites and nucleophilic sites in the same molecule. The problem is treating every site of reactivity as equally important. They're not. Every functional group has a reactivity feature that should jump out at you as soon as you see that functional group. I call this the major mode of reactivity. Not the only mode of reactivity, but the major mode of reactivity. Take, for example, an alcohol. An alcohol can be a nucleophile at oxygen and an electrophile at hydrogen. Both are true, but every time you turn the page and see an alcohol, there's one mode of reactivity that should jump out immediately. Whenever you see an alcohol, I want you to start thinking weak nucleophile at oxygen. That should be your default setting. If you can train your brain to see an alcohol and immediately see a nucleophilic oxygen with lone pairs, then you're on the right track. Now consider a carbonyl. Could the oxygen behave as a nucleophile? Sure. Could the carbonyl carbon behave as an electrophile? Also yes. In fact, later on in the course, you'll find that this alpha hydrogen is also acidic and electrophilic. But when students see a carbonyl, the first thing that I want them to think is carbonyls are electrophiles at carbon. That carbonyl is the main attraction. It's electron-poor, and it gets attacked over and over in organic chemistry. The carbonyl's major mode of reactivity is electrophilic at carbon. There are 3 possible sites of reactivity for an alkene. The pi bond has excess electron density. That makes it a nucleophile at the less substituted carbon. And when we learn radical reactions, we will find that this hydrogen can be abstracted in a radical mechanism. And we can also add a radical to this less substituted carbon. But by far, the major mode of reactivity of an alkene is nucleophilic at the less substituted carbon of the pi bond. There are entire chapters where the alkene acts as a nucleophile to attack an electrophile. When you see an alkyl halide in the future, the first thing that should stand out to you is the halogen can be a leaving group. And that means there are 2 electrophilic sites on this molecule. The carbon bearing the leaving group can be an electrophilic carbon, and the hydrogen on the carbon adjacent to the leaving group can be an electrophile. Here, the major mode of reactivity is being an electrophile at the alpha carbon, although that beta hydrogen being an electrophile is really not that far behind. So our goal here is that eventually you'll develop an intuition. I want you to gain some reaction instincts. Not memorization, but you can feel it in your soul. Carbonyl, electrophilic at carbon. Alcohol, weak nucleophile at oxygen. Alkene, nucleophilic at the less substituted carbon. Alkyl halide, electrophilic at the alpha carbon. These first impressions will immediately allow you to propose who might react with who when given a certain scenario. So your 3-step process when you turn the page on the exam and have no idea what's going on. First, what is the likely nucleophile? Who has the excess electron density in this reaction? Step 2, who is the likely electrophile? Where are we lacking electrons in this system? Step 3, find the specific atoms involved. Where are the electrons starting and where are the electrons ending? That's it. Don't start with the products or with memorized reactions or starting to draw random arrows. Start by finding the nucleophile and the electrophile, and the mechanism usually reveals itself from there. Take a second, pause the video, see if you can find the nucleophilic atom and the electrophilic atom in this system and predict the first step of this mechanism. Here we have acetone plus hydroxide in water as a solvent. What stands out to me is that big negative charge on hydroxide. The oxygen of hydroxide will be our nucleophilic atom. It has the excess electron density. The next thing that stands out to me is my starting material is a ketone. I know things about ketones. The major mode of reactivity of carbonyls is electrophilic at the carbon atom. And that works out really well because the whole point of organic chemistry is nucleophiles attack electrophiles. And now you've identified the most important bond-forming event in this entire mechanism before drawing a single arrow. And that's exactly the skill we're after. Again, this is beyond the scope of this video, but now these electrons in hydroxide can attack that carbonyl carbon. That makes 5 bonds too much electron density around that carbon, so we'll break the carbon-oxygen pi bond and push those electrons up onto the oxygen as a new lone pair, forming the first intermediate in this reaction. What do we do from here? We start over again. What jumps out to me now, even though I may have never seen this before, is the negative charge on this oxygen atom. This oxygen is probably now a nucleophile. And looking around for some kind of electrophile I can attack, I see the acidic hydrogen in water. We can do a Bronsted acid-base reaction where the lone pair on the negative oxygen atom takes a proton from the water molecule. That puts a proton on that oxygen, neutralizing that oxygen's negative charge. And that forms the product of this reaction. We didn't have to memorize this reaction. You may have never seen this reaction before, but because you can find nucleophiles and electrophiles, you can intuit your way through each step of the mechanism. And that's exactly the skill that we're after. If there's one OChem non-negotiable that opens up the entire rest of the course for you, it's this. When you look at a new reaction, immediately start finding where the electrons are and where the electrons want to go. Find the nucleophile, find the electrophile, and find the reacting atoms. If you can do those 3 things, you're no longer just staring at a reaction hoping something comes to you. You're actually reasoning through it. At its essence, organic chemistry is a predictive science. If you can conquer this skill, organic chemistry stops feeling like memorization and starts feeling more like problem solving. If you'd like the next logical skill after this one, a great follow-up is understanding exactly what curved arrows mean in a mechanism. Because curved arrows are simply the visual representation we use to show electrons moving from nucleophiles to electrophiles. Keep up the great work, ninjas.
Thanks for training with us today, ninjas. Check out this other content to see if you can level up even further. As always, don't forget to like and subscribe.